Okay, so this is on the set, the introduction set. And it says a manometer measures a pressure of 104. So we have this kind of setup. This was last Thursday, maybe. Okay, and we had a difference in height. We're trying to calculate the height. And the atmospheric pressure is 101.33 kilopascals. And the pressure that we're measuring is 104.0 kilopascals. The liquid is mercury, and we want to know what's H. If the liquid is mercury. You happen to have that solution in front of you? You know what the density of mercury is? I know I did that in the solution, but yeah. 13,000 something? Yeah. Okay, so the density of mercury is 13,690 kilograms per meter cubed. And the easy way to do this problem, the way that I did problems like this in class, excuse me, is I use the fact that, well, we know that the pressure here and here are the same. And we know the pressure here is the atmospheric pressure. What are the requirements for, so I said the pressure here is P. What are the requirements for us to know that that's P? So remember, this is one of the things that we know about pressure in a fluid under two conditions. What are the two conditions? Continuous, so yeah, it's all connected. And what's the other one? It's not moving. Not moving, yeah. So then from there, we just know that the pressure, P, is equal to the atmospheric pressure plus rho g h. And so that's pretty easy. I did it in the solution a different way, and I left off a term too, so it's wrong. I was thinking about it when I did the solution. Well, let's get a number for this. So we have 101, 330 plus 13,690 times 9.81 H. And this pressure P we know is 104,000. So what do we have? 2,006. Don't help me. 670 is equal to 13,690 times 9.81. And so what do you get for H? Okay, H is equal to 0.02 meters, 2 centimeters. You can also think of it in terms of forces. This isn't a very good way to do it, but I think thinking about problems like this multiple ways is kind of a good way to wrap your head around how all these ideas fit together, forces, pressures, etc. So let's just isolate the column of mercury from here to here, and just think about all the forces that are acting. Okay. So what forces are acting? First, there's weight, and that's at the center of mass. And the weight is the density times the volume. That gives you the mass, and then times g. What forces are acting up from the bottom? Yep, but that's right. So it's that pressure P acting up, but pressure is not a force. So how do we figure out the force? Yeah, pressure times that cross-sectional area. And then the same idea here, that cross-sectional area is the same. So that's the atmospheric pressure times the cross-sectional area. And now that we have these A's appearing, we can, it makes sense that we'd want to represent this volume in terms of A2. This is our height H. And so we can rewrite this as rho A H times G. It's at rest, so Newton's second law in the y direction says negative atmospheric pressure times the area minus rho A H G. Going the other direction now, so plus P times A is equal to 0 because it's at rest. And all the A's now, you can divide both sides by A, and you get this equation that says P is equal to E atmosphere plus rho A G, which is, what we started with the other approach. What? Rho, yes. Dang it. Anybody have any other homework questions? All right. So last time we talked about a few ways of calculating W. So let's say that we have oh yes. So let's say we have this big volume that's separated by a plunger, and this thing can be moved around mechanically by a motor. We have a gas over here and a gas over here. And let's say the pressure in gas 1 is 1.0 times 10 to the 5th pascals. The pressure in gas 2 is 0.6 times 10 to the 5 pascals. And let's say that those constant pressures are maintained. as the volume of gas 1 goes from 0.1 cubic meters to 0.05 cubic meters. And the volume of gas 2 goes from 0.1 cubic meters to 0.15 cubic meters. Okay, so first, if the system is gas 1, what's W? Now we're talking about that thermodynamic sign convention for W. And second, if the system is gas 2, what's W? Okay, before we go into solving it, how would you do this? How is it possible that those pressures would be held constant as that barrier moves to the left? Physically, how would you do that? Yeah, that's right. So what temperature would have to go up? What temperature would have to go down? Yeah, so if the pressure is going to stay the same as the volume increases, this one has to get hotter, and this one has to get cooler if it stays the same pressure as the volume decreases. Okay, let's take a few minutes, see if you can work through this with each other. Feel free to move around, talk out loud, make loud exhortations. Ask me questions if you get stuck, and then I'll go through it when you're done. Okay. You and you and you, shut up! So for part A, the system is gas 1. Work is the integral from volume 1 to volume 2 of P dV. That pressure is constant. So which one is gas 1? 1 times 10 to the 5 is the pressure. So, and the volume goes from 0.1 to 0.05. So we're going to integrate from a volume of 0.1 to a volume of 0.05 of 1.0 times 10 to the 5th dV. And so that's 1.0 times 10 to the 5th times the quantity 0.05 minus 0.1. And that comes out to be negative 5,000 joules. Does it make sense that W is negative here? Yeah, because that gas is being compressed, and so the work is negative. And then the second one, do the same way. So this time the volume of integration, the boundaries of integration are 0.1 to 0.15. The pressure is 0.6 times 10 to the 5th, and then times dV. So you get 0.6 times 10 to the 5th times the quantity 0.15 minus 0.1. And this time you get a positive answer of 3,000 joules. Does it make sense that that one's positive? Yeah, because it's expanding. What about the fact that they're not equal and opposite? Does that make sense? Yeah, because this is not an isolated system. There's energy being put into this combined thing by the motor or whatever. Um, like we were just talking about a minute ago, if this thing was just free to move, it wouldn't go this way. The higher pressure over here would push it back this way until those two pressures met somewhere in the middle. So there has to be some external work done by the motor to push it that way. And so that's why you don't have an energy balance. So all the examples we've done so far, I think we've just done two. Have assumed that the pressure stays constant during the process. That makes the math easy, but it doesn't. It's not usually a valid assumption. If you think about what you need to integrate PDV, you don't need that pressure to be constant. You just need to be able to express that pressure as a function of volume. So that's not usually true, but you can still integrate PDV if you have P as a function of volume. So how would you know the pressure is a function of volume? Well, a lot of times if a gas, if a gas is in equilibrium, some modified version of the ideal gas law can give you a relationship between those. So you often can do this. I mean, right? Pressure is a function of volume. If you assume process like progresses from equilibrium state to equilibrium state. At each point along the process, you're in equilibrium. That's not true, but a lot of times it's pretty close to true. So it goes from equilibrium state to equilibrium state throughout the process. Those are called quasi-static. And it basically makes the assumption that you're letting this process happen slowly enough that you make a tiny little increment of a change, and then you wait for everything to reach equilibrium, and then you make another tiny little change, wait for equilibrium. And so here's an example where we would use that quasi-static assumption. Actually, I have this differently in my notes. The textbook is calling it quasi-equilibrium. Let's call it that. Quasi-equilibrium. Okay, so as an example, assume this process is quasi-equilibrium. And with that assumption, in this case, we're going to assume that the pressure times the volume to the power of 1.2 is a constant. And we're going to assume that at the starting point, the starting state, pressure in the gas is 3 bar. 1 bar is 1 times 10 to the 5th pascals. So this is 300,000 pascals. And the starting volume is 0.1 meters cubed. And then it progresses to a pressure. Oh no, we're not given the pressure, but this process happens until the new volume is 0.2. So what's the W for the gas? First of all, is W going to be positive or negative? Yep, it's expanding, so it's going to be positive. We know that there's this relationship. This product is a constant, but we don't know what that constant is. We can figure it out, though, based on the starting pressure and volume. So at the starting point, $300,000 pascals times 0.1 to the power of 1.2 equal to C. Can someone calculate that? 18 what? 0.7. Okay, so now we know that this relationship, so P times the volume to the 1.2 power is equal to 18,928.7. And so that tells us that we can write pressure as a function of volume as 18,928.7 times V to the negative 1.2. And so now the work is the integral of this. I guess I'll pull the constant out. So 18,928.7 times the integral of V to the negative 1.2 dV. And the boundaries of integration are 0.1 to 0.2 for the volume. And so that's 18,928.7 times V to the negative 0.2 divided by negative 0.2. And that's evaluated from 0.1 to 0.2. And can someone calculate that? Okay, 19,474.4. 174.4. Okay, joules. And it's, oh, okay, 19,417.4. Okay, and we get a positive value like we expected with the gas expanding. Okay, so that quasi-equilibrium idea is how we're going to use relationships that we know about gases, so that we can figure out what the pressure is as a function of the volume. So there's really one more big thing that we have to add before we can start doing what we think of as thermodynamics. We have to start talking about thermal energy. So far, everything's just been mechanical energy and just sort of maybe some sort of new formats, a new way of thinking about it. But so there are going to be two things that we're going to, two concepts related to thermal energy that we have to talk about. Just like when we talked about mechanical energy, we talked about the property of energy, kinetic energy, and we talked about the change in energy that happens over a process due to the application of force, and that's work. And we have to do the same thing here. Internal energy internal energy is going to be written as capital U, and that's related to the motion of molecules within the system. If you increase the temperature of any material, you're increasing the motion of the molecules. And so internal energy is always going to be closely related to temperature. Increasing the temperature is always going to increase internal energy. This capital U is an extensive property. So the total, like if we're using this capital U, we're talking about the total internal energy in our whole system. It's a property. That means that at a single instant in time, that's a descriptive, that's a description of the system at that instant. Lowercase u is the intensive property, and that's the internal energy per mass. And then we'll also use lowercase u over bar. That's also an intensive property, but that one means internal energy per mole. Okay, so that's the property. And now we have to talk about the change in energy, and that's heat. So heat is a change in energy due to a temperature difference. We're going to represent that with capital letter Q. And notice this works the same way that it does with work. Heat is not a property. There's no such thing as an amount of heat that an object has at an instant or an amount of work that it has. That's a description of something that happens during a process. That's a change in energy. So Q is not a property. It's a change in energy. So now that we've defined these, I can give a new updated form of conservation of energy. Yeah. Okay, so here's the new updated first law of thermodynamics. Change in kinetic energy plus the change in internal energy is equal to Q minus W. One thing to be careful about here is the way I'm thinking about it, this W includes the work by conservative forces. So it includes the negative change in potential energy. Or you could also think of it as the change in kinetic energy plus the change in internal energy plus the change in potential energy is equal to Q minus W, where this W doesn't include the work of conservative forces. I like to think of the change in potential energy as just being part of the work of everything. It's think of conservative forces as doing work that's easy to calculate through potential energy functions, but be sure that you sort of understand that distinction. Does anyone have any questions about it right now? What I'm saying there with the potential energy? And notice this about the sign convention. So we have this shows our funny sign convention for work. These are increases in energy. Over here, this has to be increases in energy then too. This is energy added through heat. But W is energy lost by doing work. And that's what the negative sign is there. And so here's how to think about so notice. The sign conventions for Q and W. Just remember that Q and W are both positive for a heat engine. A heat engine gets energy added through the boiler. So energy is added to the gas through heat. And energy is removed from the gas as the gas does work. So now this is a complete description for thermodynamics of the first law. Really, the main thing that we're going to add from now on is ways to calculate these things for different materials. Okay, so if you're given a temperature change and a volume change, and you know the gas, how can you calculate the change in internal energy? How can you figure out how much work is done? Okay, and then we'll plug those complicated things into this sort of simple formula, but this is the basis of it. Okay, so heat transfer occurs in three ways. Conduction. Anybody know the other two? Convection. Yep. What order do I have? Radiation and convection. So I'm going to go through little descriptions of these. There's going to be one equation associated with each one of them. So the first one is conduction. And when heat is added through conduction, energy is transferred particle to particle through a material. Without those particles changing their locations. So, you know, an example of that is an iron pan. You heat up this part, but the handle gets hot, and you know, none of the atoms in the iron are moving from here to here, but you get vibrations in the atoms here. You cause the things next to it to vibrate, and that energy is transferred out here and raising the temperature.
So what does that say? Transfers through metal?
Transferred through material, the particles of the material. So in this case, the material particles are the atoms in the iron. One thing that means is you can't have conduction without a medium to carry the energy. There's no such thing as conduction through a vacuum. And the rate of heat transfer through conduction works through an equation called Fourier's law. And that says the rate of change of heat transfer, the time rate of change of heat transfer, is equal to a constant kappa times A. That's a cross-sectional area. I'll explain what all these mean. Times basically the gradient in temperature as you move along the path of the energy. Okay, so kappa is a material property called thermal conductivity. You can, you know, just Google thermal conductivity of iron or whatever material. A is a cross-sectional area perpendicular to the flow of energy. To the heat flow. And X has to be set up, the direction of positive X is towards the lower temperature, because conduction always happens from the high temperature toward the lower temperature. So that's the direction that the heat's moving.
So,
Mhm.
make sure I understand this correctly. So A, for example, in the diagram above would be like the bottom of the pot, and then
Yeah, so it's a little confusing. Let me draw one that's easier, because with the pot, it's like turning the path of the energy. But so if you have heat conduction going along this pipe, and this is the high temperature, and this is the low temperature side, then the direction of positive X is this way, and that's also the direction of heat transfer. And this area is A. Okay, so let's do an example. What? Yes, it does have units, and you can figure it out from the equation. So this is like that's Kelvin per meter. That's meters squared. And this is watts. So that has to be like, move everything over, and you get kappa is equal to watts per Kelvin meters or something. Okay. I probably have it written here. Yeah, that's right. Watts per meters Kelvin. Okay, so here's an example. Let's say we have a 1 meter squared window. And this is the outside. And right at the surface of the window, we have a temperature of 15 degrees Celsius. And then the backside that's obscured is the inside. And right at the surface, that has a temperature of 20 degrees Celsius. And let's say the thickness of the window is 2 centimeters. That's a thick window. And if you look up the coefficient of thermal conductivity for glass, it's 1.05 watts per meters Kelvin. And so if we assume that temperature varies linearly through the thickness of the glass, what's the rate of heat transfer through the window? In other words, you could use this calculation to figure out how much energy you're losing through the window, like how much benefit you'd get out of insulating the window in the winter or whatever. Well, not the winter, unless the winter is 15 degrees Celsius, maybe in a few years. Okay, well, let's sort of get our bearings here. So let's look at it from the side. This thickness is 2 centimeters. The energy is going to be flowing this way, so that's our positive x direction. So let's call this side x equals 0, and then this point here would be x equals positive 0.02. And then the temperature in degrees Celsius at any x value. So what we're doing here is we're just coming up with a linear function that describes the temperature at any point in the thickness of this window. So when x is equal to 0, we have a value of 20. Then the slope of that gradient is, it's dropping 5 degrees over a length of 0.02. So we have negative 5 divided by 0.02 x, or 20 minus 250x. And so then dt dx is just negative 250. Which you could also just think of as the change in temperature over the thickness. I'll call the thickness L. And so now the rate of heat transfer is I skipped that negative sign. That's why I'm confused. Fourier's law needs a negative sign here. Go back and change that. That's important. Okay, so the change in heat is negative times 1.05. That's the coefficient. Okay, 1.05 times the cross-sectional area times dt dx. And so you get 262.5 watts, or in other words, every second, 262.5 joules. One thing to be careful with this conductivity equation and with all of these heat transfer equations is that Fourier's law gives the transfer of heat, or the time derivative of the heat in the direction of that increasing x. then you have to think about the translation from that sign convention into the sign convention where Q is positive if your system is adding energy. There's no, there's no given relationship between the direction of positive X and whether your system that you chose is gaining or losing energy. Okay. So that's unrelated to the thermodynamic sign convention for Q. Not Q factorial. That's supposed to be like, yeah. Any questions about that? Yeah.
You want us to labor an answer and block?
I guess I don't care.
Then kappa was in Kelvin and we used Celsius.
Yeah, because it was a change in temperature. We're talking about a derivative of temperature, which is a rate of change. And so remember, changes in Celsius and Kelvin are the same.
Okay.
Yeah, so those are this. Doesn't matter. 262 joules, is that a lot or a little? It depends what your standards are. But how many joules of food energy do you eat per day? 8 million. So a joule is pretty small. Okay, the next type of heat transfer is radiation. And the way radiation works, any material that's above absolute zero Kelvin, it's electromagnetic waves. And these waves carry energy, and that's radiation. In the universe, yeah. I guess that's sort of a philosophical question in a way. But I mean, like, I forget the number. It's like the average temperature of all the things in the universe is like a tiny, tiny fraction of 1 Kelvin, because there's just so much empty space. Well, yeah, I mean, there's just like this amount of all of the energy that happened in the Big Bang or whatever is spread out over such a huge amount of space that far out in space, like, yes, apparently there is stuff that's essentially absolute zero, but not on Earth, And I'm already getting that's already getting like over my head as far as physics. You should ask Tony about that if you're curious about it. He'll give you the real answers. But on Earth, yes, everything is above 0 Kelvin and everything emits radiation. That's radiation. Electromagnetic waves can travel through empty space. Um, and so radiation doesn't need a medium to travel through. And it's the only one of these mechanisms for heat transfer that don't require a medium. Conduction and convection, that can't work through space. Radiation does. Yeah, right. Those electromagnetic waves are particles in some applications and waves in other applications, and that's photons, yeah. So radiation doesn't require medium, and there wouldn't be any life if that weren't true, because we get all our energy from the sun through empty space. When radiation is another material, some is transmitted, some's absorbed, some's reflected. That's true for every material, but the relative amounts of those are different from material to material. Some's reflected, some's absorbed, some's transmitted into the material, or transmitted through the material to other materials. And we have an equation for the amount of heat that's emitted from a material. This equation is called the Stefan-Boltzmann law. And this equation says the time derivative of the heat sub E for emitted is equal to a constant that represents the material times a universal constant times the surface area of the material times the temperature to the fourth power. This epsilon is called the emissivity. And values of the emissivity range from 0 to 1, so it's just kind of it's a measure of the material's tendency to emit heat. For example, it's really high, it's close to 1 for a matte black material, and it's very low, close to 0 for a shiny white material. So this would be shiny white. This would be matte black. The constant sigma. Oh, and this is unitless, by the way. Sigma is called the Stefan-Boltzmann constant. And it's equal to 5.67 times 10 to the minus 8 And then the units you could get from just, rearranging that formula, but it's watts per meter squared Kelvin to the fourth. Again, notice that you can't trust that sign when you're using it in thermodynamics equations. The same thing happened with conductivity. A positive value of Q dot emitted just means that that object is emitting that amount of energy. So depending on what your system is, that might be the sign you want, it might not be. Okay. Any questions?
What exactly is A in this case?
Oh, A. I meant to write that. A is the surface area. So, a marble at a certain temperature can't emit as much energy as a beach ball. Okay, and we have another equation dealing with that. I'll talk about that on Tuesday. I will get the next problems posted tomorrow. Okay, probably won't today. All right, have a good weekend. Enjoy Monday. Well, wait, in a somber, reflective way.